All right, now we're going to talk about circuits. So now we're going to be putting together everything we've really been talking about the last couple days, and now use it to analyze direct current circuits. By direct current, I mean that we're going to have circuits that are connected to constant power sources that want to drive current directly in one particular direction. This is in contrast to alternating current, where the direction of the current can actually oscillate back and forth. And I'm guessing Professor Rosario will talk about that a little bit more later in the semester, because you need to do some stuff with magnetic fields first before you can talk about alternating current. For right now, we'll talk about currents that usually things will be hooked up to batteries or direct power sources where a current can be driven in one direction. The next two lectures are going to focus particularly on batteries and resistors, so things that can draw energy from current. We're going to ignore capacitors for right now because they make things a little bit more complicated, because with capacitors, current can be time varying. And for at least the next two lectures, we want to try to understand current in circuits in the case where the established current that is set up along all the wires that make up your circuit will be some constant value. So again, to remind us of some of the stuff we've been talking about, we're really going to be concerned with three elements in building all our circuits. The first will be just the wires, which in this case, we're going to treat as just conducting elements that charge can easily flow down. Wires have a very small internal resistance. I think we actually calculated it on a problem earlier today. But for ideal circuits like what we're going to be drawing, unless the problem says otherwise, we're going to always assume that the wires have a negligible internal resistance. So the wires themselves do not resist current in any way. In contrast, we will be including things like that we are going to generally just call resistors. And these are devices that will be able to draw energy from the current, and they themselves resist the flow of current, hence the word resistors. We will see and talk about more, though we really have already seen this when we talk about conductivity and resistivity, that these are objects that resist the flow of current. And for what we're talking about in these circuit diagrams, what we're doing in the next two lectures, again, we're going to always assume ohmic resistors. So in that case, I'm going to be able to state a resistance capital R, and it's going to be assumed that that is always the resistance, even if the potential difference in current changes across the object. And finally, we're going to be concerned with batteries. And batteries, using our mechanical analogies, again, we can continue to think as objects that pump up charge and generate a potential difference within the battery itself. You know, a very classic old school battery or a simple electric cell might be something where you have two electrodes that are immersed in a sulfuric acid component. One of the rods, I believe traditionally, was zinc, and the other rod was a carbon tube. And the way that worked to establish a potential difference inside one of those batteries is that the sulfuric acid would dissolve some of the zinc electrode, which would result in positive charges. Let's see, let me make sure I'm remembering this correctly. Right, it ends up dissolving, the sulfuric acid would dissolve some of the zinc atoms, and so the zinc atoms would leave the zinc kind of nucleus would kind of pop off and leave electrons behind on the electrode, so that the zinc rod in the cell would take on an overall negative charge. And then the sulfuric acid itself would have an overall positive charge. And so then that electrolyte solution, the sulfuric acid, actually then was able to interact with the carbon electrode and pull, that solution of positively charged sulfuric acid would pull electrons easily off the carbon electrode. And so as a result, you would have two electrodes that have different charges. I have no idea why I'm not just drawing this. And so this is kind of a simple kind of battery cell. And this was immersed in some sort of sulfuric acid. And so again, the sulfuric acid would take positive charges off the zinc, which would create a overall negative charge on the zinc rod, and then that positively charged sulfuric acid would pull electrons off of the carbon rod, which would leave the carbon rod overall positive. So now you have two conducting electrodes that have a charge difference between them. That, of course, establishes an electric field, that establishes a potential difference across the two, and then you might hook the positive end of the terminal of your battery up to the carbon tube, and that would go off. And then the negative end of the battery would be connected to the zinc, and then that would go off and do something else. So that was kind of the simple, that's kind of an old version of kind of what a battery looks like. Looks like my screen shifted. There we go. And again, the point here is that when we're thinking of batteries is that we're treating them as things that create a potential difference in the circuit. And then that potential difference can also be thought of as giving charges potential energy. So as they march off, they have energy that they can then do work with, which might be light a light bulb or doing something else. Historically, I noticed your book still uses this term, though I think it's getting a little dated. Historically, this was viewed as the battery or the power source would be treated as an object that's applying something that used to be called the electromotive force or the EMF. So a 9-volt battery, for example, the idea there is that the 9-volt battery would be providing a 9 volts worth of quote unquote electromotive force that would allow the charges to travel. I don't think that's used as often as it used to be, which is kind of a shame because I kind of liked calling the power source, an EMF source, because rather than pronouncing EMF, I always thought of it as oomph, which I think kind of intuitively is kind of nice because it is indeed the battery that's giving the charges a little bit of oomph to push them to travel in some sort of current along the wire. And we are more or less always going to be thinking of ideal batteries, which the ideal battery is one where we, again, are ignoring any sort of internal resistance within the battery itself. Real batteries, of course, usually also have some small internal resistance, little r. All right, so for current to flow, we've seen that we need to establish an electric field inside a conducting wire. That is established because of a potential difference where the battery can, a battery can play that role in providing that potential difference. But it also requires there to be a full circuit. There has to be a potential difference through the circuit, else there is no reason why current will want to flow. It will just establish an electrostatic configuration. The dumbest example might be just a loose wire that's not connected to anything that provides a potential difference. There might be positive and negative charges that can flow, but there's nothing that's driving them. So if there is any net charge that's on the wire, then those positive and negatives will then just redistribute themselves into some sort of electrostatic configuration. And it would just more or less be random motion, if anything, which we saw does not create a current. You could also take the example of, say, an open circuit, where maybe I have a battery that's connected to a bulb, but it's not a complete loop. Now, in order for the light bulb to light up, there has to be electrons that are, if I'm thinking of the electrons as what's carrying the energy down a copper wire, there has to be charges that are flowing down the wire through the light bulb and depositing some of their energy into the light bulb. But again, if these are perfectly conducting wires, there's no reason why current is going to want to flow. Even though there's a potential difference set up across the battery, the wires, and in this case the light bulb, are attached to one end of the battery. So the wires are just going to get some sort of uniform distribution of charge across them, and they will just, again, become an equipotential surface along with the positive end or the negative end of the battery, and it will establish itself into an electrostatic situation. What actually does produce a current is when you have a closed circuit. Because in that case, if we think of it as, if we take the conventional current approach, where it's actually positive charges that are doing all the moving, then in this case, you can imagine positive charges will see a potential difference across, the entire wire. They will see themselves at some high potential difference, say here, but then across the wire, they will see that traveling across the wire, they will go down to some lower potential difference. And so that potential difference establishes an electric field, and the charges will have a reason to come out of the battery at the positive end and start moving their way around the wire, which will include them going through the light bulb, and then they can deposit their energy into the light bulb. And if they deposit enough, the light bulb will light up. And so then as the positive charges make their way around, once they get back to the negative end of the battery, they then go through another pump where an electric potential difference is reestablished, and then those charges march off from the top of the battery again and repeat and repeat. So we are going to be looking at that in some detail today. I'll just say as an aside, just because I noticed it's defined in your book. When we say the electromotive force, which again, just think of it as that is the potential difference that is established to the charges as they go through, say, a power source like a battery. It can be defined as dWdq. The amount of work that is being done on the charges as they move through this pump or this battery or whatever it is. And notice that this has indeed units of volts. So again, you can think of it as, for example, a 9-volt battery means that there's being 9 volts of quote-unquote electromotive force being supplied to the circuit. Though it's a little bit misleading because it's not really a force. All right. Let's see. Now, I think I talked about this yesterday, but I'll just repeat it for good measure. The way I like to think of it is kind of an escalator analogy of how circuits work. Is that you can think of a battery or a power source lifts charges up to a higher electric potential by doing work on the charges. You can, and again, I like to think of this as, maybe like a ski lift or an escalator. If you think of an escalator, if there's some charge Q that gets in at the bottom of the escalator is doing work to move it up to some higher elevation. This is kind of, if you want to try to draw an analogy with gravitational potential energy, the escalator is rising the charge up so that then once it gets to the top of the escalator, the charge has done some work, and now that charge has some gravitational potential energy. The analogy is that the battery is pumping up the charge so that the charge leaves the battery with a higher electric potential energy. And then the idea is that once it gets to some higher electric potential, it is then free to kind of roam around at that potential. And that would be the analogy of it kind of going through a wire until it gets to something like a resistor where it will have to bombard it. It will lose some of that energy. So you can think of that as maybe it's a kind of a bumpy ride down where it goes back to lower elevations. Then once it gets past the resistor, it continues traveling through the wire and when it gets back to the battery, it is back to where it started. So again, the idea is that it's lifted up, the battery does work, it then has some higher electric potential energy. it travels around. Once it reaches something like a resistor, some of that energy can get dissipated, and then it is brought back down to a lower potential or lower potential energy until it gets back to the battery, and then it's pumped up and it repeats itself. The way this is drawn, again, what's important to note here is that every time the charge is making a full loop around the circuit, it is returning back with a potential or potential energy that was exactly the same as what it started with. And this is really saying nothing more than just a statement of energy conservation. You imagine that something bad would occur if, let's think if I could do this with simple numbers. Like suppose a battery supplies 20 volts to the charge every time it goes through the battery. But then as the charge moves around the circuit, it only loses 10 of those volts through a light bulb or something like that. So it would go through a battery, it would get 20 volts, it would give away 10 of them, and then get back to the battery, and it would still have 10 volts left over. Then it goes through the battery again, it gets 20 more volts. Now it has 30 volts of energy. It gives away 10 in the light bulb, gets back to the battery, gains 20 more. So now it has 40 volts. You can kind of see where this is going. Every time the charge would complete a loop, it would get more and more and more and more energy. That actually would result in the current getting faster and faster and faster because there's nothing that is able to kind of limit the current or stop the current in that case. And in that case, it actually would be, say, the tiny resistance of the copper wires would be what finally stops the current from just getting faster and faster. And that would be an example of a short circuit. Because since that resistance is very small, the current would ramp up and up and up until that resistance finally was able to stop the current, or the power generated in the wire made the wire melt or something like that. So let's see, to summarize, the change in voltage, or if you want to think of it as electric potential energy, is 0 throughout the circuit. If not, the current would be unable to remain steady. Let's look at this using a very simple example. So here's my battery. And then it's connected to some sort of resistor. Suppose a light bulb. And it's a complete circuit. What is going on? Suppose this is a AA battery, so it's 1.5 volts. And this light bulb has some resistance. Just say it's 100 ohms or something like that, just to keep the numbers simple. So if I wanted to follow an individual charge, and again, we're always going to take the conventional current approach where the charge, the current is actually the flow of positive charges. So if this is the positive terminal, the current is going to want to move in this direction. I'll draw a little I there to represent the direction the current is moving. Again, we can think of what's going on is that you have some charge that moves through the battery from the negative terminal to the positive terminal. Taking the conventional current approach, you're going from low potential to high potential, which is actually the opposite of what positive charges want to do. Hence, therefore, the battery has to do work in order to get that charge up to a higher potential. In this case, say going from 0 volts to 1.5 volts. That charge then takes that energy and starts to roam around until it gets to a resistor where it can deposit that energy and then continues to roam around until it gets back to the battery, then gets pumped up again. The battery does work and then it repeats itself. If it had extra energy left over, then the current would just start to get faster and faster and faster until it reaches some sort of balance or steady state between the energy that's being put in from the battery and the energy that's being taken out from whatever else is in the circuit in that case. So the current then establishes a steady state throughout. Also, it's worth noting, because sometimes this is a misconception. Notice I've drawn only one eye to represent the current everywhere. I am claiming that the current, whatever it is everywhere in the wire, and that includes the part of the wire that's before the light bulb, and it's the same exact current that is going through the wire after it has moved through the light bulb. And you can think, why must that be the case? Rather than thinking of it in terms of energy conservation, you can think of it in terms of charge conservation. If more electrons were entering the light bulb than were leaving the light bulb, that obviously is not going to be a steady state situation. Then electrons are going to slowly build up within the light bulb, and eventually, though, that buildup of charge would start to affect the current. So you can't have a steady current without, the current in this case has to be uniform everywhere. Even though the energy of, say, the electrons or the positive charges or whatever is the charge carrier might be changing, it must adjust itself. Maybe the charge carrier density increases if the drift velocity is decreasing. They will adjust themselves so that the overall current remains constant everywhere throughout the circuit, as it must, again, by charge conservation. You can't have more electrons leave the battery than what returns to the battery. Or similarly, enter or leave any sort of item along the circuit. Something we're also going to have to get used to doing is translating kind of these cartoon photos into circuit diagrams. So you saw a little bit of this with capacitors, where we represent batteries by these two uneven lines, the longer line representing the positive end and the smaller line representing the negative end. Wires just go out. And for resistors, we write them as kind of jagged lines. So this is the resistor, in this case, equal to 100 ohms. And then this battery, we can say has some potential V, which in this case is 1.5 volts. Then if I were to draw the current, I might draw the current like this. The way I've drawn it, again, the convention is that it's, current flows out of the positive terminal. It goes from the positive terminal out through the light bulb, and then back to the negative terminal, and repeats. And so again, this might be getting redundant at this point, but we can again look at what is going on with how the potential is changing throughout the circuit and convince ourselves that any potential that is gained from the battery must be lost by the resistor. If I label the corners of this circuit A, B, C, and D, then also again go back to my highlighters where I can highlight equipotential surfaces. I know this conductor that is attached to the positive terminal, that makes this thing in blue an equipotential surface. And then similarly, the part that is connected to the negative terminal is also an equipotential surface. And by definition, the potential difference as you go from D to A, so this is D to A, is in this case 1.5 volts. Work is done as you go through the battery from the negative to the positive terminal in a way that the amount of work that's done, call it the electromotive force if you want, the oomph, EMF, there is 1.5 volts of energy, 1.5 volts supplied to the charge carriers in that case. The voltage difference from A to B is just 0 because it's along it's an equipotential surface. There's no change in the potential along from A to B. From B to C, we can see that this must be written as negative 1.5 volts. If you go back to the battery, when we went from the red color to the blue color, which in that case was going from negative to positive, it was plus 1.5 volts, so red to blue was plus 1.5. So then as you go from B to C, you're going from blue to red, so it must be the same, but opposite sign of negative 1.5 volts. And then from C to D is an equipotential surface. They're both colored red. That change in the potential is 0. So then notice, what do you get when you add up all the potentials differences as you go throughout the loop? That is just from D to A, plus from A to B, plus from B to C, plus from C to D, and then you're back to where you started. But then notice that's 1.5 plus 0 minus 1.5 plus 0 equals 0. In completing one loop, there is no overall net change in the potential. Whatever is gained through batteries is lost elsewhere. And this must be the case even for more complicated circuits. So suppose I had a battery this is plus V of the battery. And then I have 2 resistors, maybe 2 light bulbs connected in series, like a really poor person's string of Christmas lights with only 2 lights. So this might be resistor 1 and resistor 2, and there's some potential difference across them. We can even give some colors if we wanted to. Again, we said this terminal has some potential difference. This terminal is at some other, but now there's this intermediate region here, which will make another color, green. So in this case, when you go from red, so let me give some letters actually, A, B, C, D, E. When you go through the battery, so from E to A, you gain some potential, whatever the voltage of the battery is, 1.5 volts, 9 volts, whatever. The voltage from A to B obviously is going to be 0 again, so I won't bother with that. The voltage from B to C is some value, so we'll say it's VR1. The voltage from C to D is some value, which we'll say is VR2. And clearly the voltage from B to D, so I go all the way from the top to all the way from the bottom, must be the same as VBC plus VCD. Just by looking at just based on the colors. The voltage from B to D is you're going from blue to red, which must be the same as going from blue to green and then from green to red. But the voltage from B to D, if going from red to blue was plus the voltage of the battery, this must be minus the voltage of the battery. So again, you see if you sum over all the potential differences across the entire loop, you have the voltage from E to A, the voltage from A to B, B to C, C to D, D to E. A to B and D to E are just zero because they're just wires along an equipotential surface. But we just said that B to C and then C to D is the same thing as B to D. From E to A, that was plus the voltage of the battery. Then from B to D, that was minus the voltage of the battery. So again, the change in potentials across the entire circuit add up to zero. And if you think of this in terms of potential energy, it's the same exact expression. The change in potential energy is through, say, the power delivered. If you looked at the sum of all the powers, you would again get this relationship. All right, so what I'm going to do is this allows us essentially, the conservation of charge and the conservation of energy allow us to write essentially the only two rules you need to understand any circuit. So these are called Kirchhoff's circuit rules, after Gustav Kirchhoff, I think is his first name. So the first rule, which is just a statement of conservation of charge, is called the Junction Rule. Again, this is just conservation of charge. And all this says is the total charge going into a junction must equal the charge coming out. We kind of argue that this must be the case for individual elements. The charge going into a resistor must balance the amount of charge that's coming out of the resistor, else that is not going to be a steady state situation. Where we will actually see this applied more in practice will be tomorrow's lecture, where you might have some wire that has, at some junction, maybe it divides out. So then there are two different wires that the current could travel down. So there might be some current I1 that comes in, but at the junction, that current might divide out. So some of those charges continue going to the right, but some of those charges might change their path and start going south, or towards the bottom in this case. And all the junction rule is saying is the charge that goes in, or I1, must equal the charge that is coming out. There must be a balance with, the amount of charge with arrows going into the junction must balance the arrows that are going out of the junction. So sometimes I might write this like this. The sum of the charges in must balance the sum of the charges out. And again, these junctions could be, as complicated as your heart can dream. You might have another fourth one here, which might have a current I4 that's also coming in. In that case, then this would just adjust to be I4 plus I1. The two that are coming into the junction must balance the currents that are coming out of the junction. We'll see that more tomorrow. The big one is the loop rule, which again is really just a statement of conservation of energy. The way to write that is any, and I'll underline any loop traversed along a circuit must have no net change in potential. The way we might write this down is the sum of the potential differences across all the items in some loop that you draw must equal 0. For the examples we did, there really was only one loop you could draw, and for most of today's lecture, or actually I think for all of today's lecture, there will only be one loop you could draw. But once you start getting into more complicated circuits, there might be different kinds of loops you can draw. I'll save that for tomorrow. All right, I'm actually going to copy this. So I can write this all on the same page. So I guess this all deserves a highlight. All right, so let me write down, just so that you have a cheat sheet that you can refer to, the general strategy for any circuit problem. And then I'll do a bunch of examples. And then we'll do more examples in class. But really, you'll see that once you understand how to apply the 4 steps I'm about to write down, you can solve literally any circuit problem that we throw at you. So step 1 is to, of course, draw a picture, draw a circuit diagram. Label all the known and unknown quantities. So if you have completed circuits, likely those circuits are going to have currents flowing through them. So you might make variables that represent your resistors, your batteries. Usually the hard part for this step is to translate something into a circuit diagram. Step 2 is you have to assign a direction to the current. So along each wire, assign a direction to the current. And you might say, how do I know what direction it's going to be? Make an educated guess to the direction that you think the current is going to flow along a particular wire. The beauty of this strategy is that if you guess incorrectly, the math will correct you. So essentially, if you guess that the direction of the current is wrong, when you go through the math, it will just pop out with a minus sign, which all that means is you just drew the current moving in the wrong direction, and you just flip the arrow around. So the math will correct you. Also during the step, at junctions, if they exist, again, we'll see those more tomorrow, not today. Apply the junction rule. So if you have junctions where the current is dividing, the junction rule provides a relationship between the currents that you have flowing in and out of that junction, where you have made educated guesses as to the direction of all those currents. All right. Third step is to draw a loop in your circuit. Pick some starting point. From that starting point, trace out a complete loop where you end up back where you started at the end of the day, so that it must be a fixed closed loop. As you're drawing this loop, you will likely pass through batteries and resistors. When you do that, to calculate the potential change, use the following rules. When you're passing through batteries, write that the potential change is plus whatever the potential of the battery is. If your loop is moving from the negative to the positive terminal. So if in the direction of the loop that you just drew, it's going from the negative terminal to the positive terminal, state that that potential difference is going to be plus whatever the battery is providing, 1.5 volts or negative volt, or 9 volts. Right, the potential change is negative, the potential of the battery, if you're going the opposite direction. This doesn't depend at all on the direction you've assumed the current is flowing. This is just if your loop, the way you've drawn the loop is going from negative to positive along the battery, that's plus. If it's going in the opposite direction, it's minus. For resistors, when you pass through a resistor, there is some potential change. It's, we've talked about this, how it's the current times the resistance, V equals IR. But it can be a plus or minus depending on if you're moving in the right, if you're moving with the current or moving opposite the current. So write the potential change when you go through the resistor as minus I times R if loop is traveling in the same direction as the current. And then write it as V is plus IR if opposite. If you're drawing your loop from left to right through a resistor and you've also guessed if you've made an educated guess that the current is also moving from left to right through the resistor, you would write that as V equals minus IR. If your loop and the current are moving in the opposite directions through the resistor, you use a plus sign. With those, you can then apply the loop law. Essentially, for all those potential differences you've just calculated, whether it's from the batteries or from the resistors, you add them all up and set them equal to 0. And that gives you a relationship between various variables. And the hope and the goal is that you can do this in such a way so that there's only one unknown that you can then algebraically solve for example. I'll say as a side note, we've already talked about how when you have capacitors in series and parallel, you can establish an equivalent capacitance. Similarly, we're going to find that there are similar formulas we can write down for resistors. If you have resistors in series or resistors in parallel, you can replace them with an equivalent resistance that represents that entire configuration. So calculating equivalent C capacitances or resistances can simplify the math. Ugh, that's terrible. It's not great, but there you go. All right, so the goal now for the next 2 lectures is to get super, super comfortable with everything on this page. If you get comfortable with what is on this page, then you can solve any circuit problem out there, assuming it's batteries and resistors. So this strategy, again, I just laid it all out. A lot of it probably did not make a lot of sense, so I think the way to do it is just do a bunch of problems. So let us start. Super simple. Suppose we have some sort of battery and is connected to some device. And let's suppose this is a AA battery, so it's 1.5 volts, and this is some, maybe it's a little LED screen or something that has a resistance of 15 ohms. And the question we might ask is, what is the current that is established in this situation? The first step is to turn this into a circuit diagram. So I see that there's a battery, I see that there's a resistor, and the question is, how do I connect these using wires that make sense? Now in this case, it's actually pretty easy, because you can go back to the original drawing, or if you had a circuit actually physically in front of you, you can see that the positive terminal goes out in a single wire and connects to one end of the resistor. So I might draw that like this. What I just drew represents this part. And then similarly, it goes through the resistor and then travels in a single wire back to the battery. So then I might draw it like this. Okay, so we've established what our circuit diagram looks like. And I'll copy it down here without the colors. I know there's a V here. This is the positive end, this is the negative end. There's a resistance here. This is a closed circuit, so presumably a current will begin to flow. Now, again, you have the freedom to guess what you think the current is going to be. Luckily, there are no junctions here. There's only one circuit, one loop here. So there only can be one value for the current. It doesn't divide out anywhere. So there's only going to be one I to represent the current. But now the question is, does it go clockwise or does it go counterclockwise? And again, the nice thing here is that it ultimately does not matter what you choose. The math will fix it for you if you choose wrong. But of course, it's nice if you can always be working at positive numbers or at the negative numbers. So you might think in the conventional sense, charge is the flow, or the current is the flow of positive charge. I might imagine that the current is going to flow in the clockwise direction. So let's make that assumption. And now see what the math tells us. So maybe I'll just write that down. Guess I goes clockwise. And again, there's only one I in this problem because there are no junctions. So if this is indeed a steady current, I better be constant everywhere. Now I'm going to draw a loop around the circuit. And again, you have the freedom to make that loop whatever you want, as long as you start and end at the same point. So maybe I will choose here. I'm going to have that be my start and end point. Again, you could choose somewhere else. Does not matter. And then I'm going to follow the current in this case. So I'm going to start here. I'm going to travel out, go up through the battery, around to the right, down through the resistor, then back over to where I started. That is my loop. That I have drawn. You could say, do you have to go clockwise? No, you can go counterclockwise. We'll actually do that. We're going to do the symbol problem to death so you can see that really you do have the freedom to choose the current and the loop to be whatever you want. So as I was drawing this loop, I started here in the lower left corner. I then went through the battery. And I went from the negative end to the positive end. So I would write down, since I'm going from the negative to the positive, I would write down that that's plus the voltage of the battery, according to the rules on the previous page. If there was a charge that was moving in the same direction as the loop I drew, work would be done on that charge and there'd be a gain in potential. Then I kept marching along, and then I went down through the resistor. And I know the potential change across the resistor is the current times the resistance, but do I do minus IR or plus IR? In this case, I would say it's minus IR because notice that the current is also going from top to bottom. The current is moving from the top of the circuit to the bottom of the circuit. So in this case, the current direction and my loop direction are pointing in the same path. They're both pointing from top to bottom. So I would say then I would write that as minus V through the resistor, or minus the current moving through the resistor, which in this case is just I, times the resistance of the resistor. And again, the minus sign is because the loop and current are in the same direction. I guess I can say here, the plus is because you moved, or rather the loop moved from the negative to the positive terminal. And then once I get through the resistor, I continue back and I get back to where I started, my start endpoint of my blue loop that I've now drawn. And so that says if I complete a full loop, there can't be any net change in the potential. So to apply the loop law, I then state that this must be equal to 0. Or similarly, that this must be equal to 0. Then what does this tell us? Then this says that V battery equals the current times the resistance, or that the current is the voltage of the battery divided by the resistance of the resistor. In this case, 1.5 volts divided by 15 ohms. Or 1/10 of an amp. So in this case, we have calculated what is the current throughout this entire circuit by drawing a loop and applying Kirchhoff's laws. Which for the loop rule, again, is essentially just a statement of energy conservation. All right. Let's do it again. Again, I will assume that the current is moving. Oh, I guess I should say back here. We calculated the current as 1/10 of an amp, and notice that is a positive number. It's a positive value. So positive, which all that means is so we drew I in the right direction. All right, anyway. Now let's do the problem again. So take 2. In which case I'm going to draw a circuit diagram, step 1. I'm going to assign variables, some I know, some I don't know. I'm going to make an educated guess that of the direction of the current. I'm going to again assume it goes clockwise. This time, though, I'm going to draw my loop in the opposite direction. So maybe I'll start here, because again, it doesn't matter where I start, so this will be my start endpoint. But now I'm going to draw the loop rather than going clockwise, I'm going to go counterclockwise. So I'm going to start at my start point, loop around, and I end up back where I started. As I do this, I pass through the resistor, and then I pass through the battery. So we have to now calculate the potential changes as a result of us moving through those two. Now passing through the resistor, the thing to notice here is that now the loop and the current are going in the opposite direction. The loop is going from bottom to top, the current is going from top to bottom based on the educated guess we made for the current. So your loop and the current are moving in the opposite direction. So in that case, for the resistor, rather than saying negative IR, we would say that is plus IR. And again, this is because loop and current in opposite directions. Then I march around the wire, I eventually get to the battery, and I go from the battery from the plus end to the negative end. So I'm going in the opposite direction through the battery that we said before. And according to the rules, we then write that as negative the voltage of the battery. I loop around, I eventually get back to where I started. To apply the loop law, I set this equal to 0. And then you're probably noticing that at the end of the day, you get the same answer. The voltage of the battery, 1.5 volts. The resistance, again, 15 ohms, gives you plus 0.1 amps. Notice I'm treating all my constants, like the voltages and the resistances, the 15 ohms, the 1.5 volts. I'm always treating those as positive numbers. And then it's up to me as I apply these rules of whether I put a plus sign or a minus sign in front of them. So again, just for completeness, negative, because you're going from positive to negative terminal. Take 3. Now let's say, okay, I think actually the current is going to move counterclockwise. So I'm going to make a guess that I is counterclockwise. So my first step, I drew a circuit diagram. I then defined my variables. I made an educated guess of what I think the current's going to be. Now I'm going to draw my loop. And the previous 2 takes just showed you that it doesn't matter the way you draw the loop. So I'm going to choose this direction. And now I'm going to apply the loop laws. So if this is my starting point, first thing I do is I go through the battery, but I'm going from negative to positive. So I'd write that as plus the voltage of the battery. And then go along the wire. I then go back down through the resistor. But notice the loop is going from top to bottom, but the current is going from bottom to top. So I would do, so they're moving in the opposite direction. So rather than minus IR, I would put plus IR. Then I loop back, I get to my starting point. I set that equal to 0 by the loop law. Notice in this case, I equals negative the voltage of the battery divided by the resistance, or negative 0.1 amps, sorry. And the fact you got a negative sign this time just means you drew I in the wrong direction. So in your final answer, just flip the direction of I around. But still notice it's the correct number, it's still 0.1 amps. But the minus sign is just telling you drew the arrow in the wrong direction. And this is kind of nice because it doesn't mean you have to start over completely, it just means you just have to adjust your arrows. Yes, this was take 1. All right, let me do 2, maybe 3. I don't know how long I've been recording. I apologize if this is a longer lecture. The next lecture will be very short because I'm essentially getting it all out now and then just doing it with multi-loops. It's just more of the same. Let me do 2, maybe 3 more examples. But now let's actually make them more interesting. All right, let's zoom in. So typically in a lot of your devices, you will see that require multiple batteries. You usually have to place them kind of side by side with one another. And maybe this connects to you have a little LED screen or something that displays a word. How the Y reaches out of the LED screen is unclear, but never mind. So suppose you have two AA batteries. Let's see, how well can I write upside down? Is that correct? Oh, well done. 1.5. And usually you have to put them in kind of reverse order, and then they attach, in your LED screen or something, it attaches to the display. I've drawn that wrong. So that circuit would not work. So usually they're drawn you have to put them in upside down with one another, because usually there is a little conducting piece that attaches the negative end of one battery to the positive end of the other. So then the LED screen, there might be a connection here, and then the negative end here, there might be a connection that goes out to the screen or whatever the device is. So the first step would be, can we turn this into a circuit diagram? And with series circuits, again, it's much more straightforward. Really gets tricky when you're doing parallel. So there's one of the batteries, and it's connected in series to another one of the batteries. And then that connects to some LED screen, which we're going to say has some resistance, 1.5 ohms. So here's the voltage of the battery, and this is some resistance of 1.5 ohms. So that might be the circuit diagram I draw in this case. And again, if doing the colors is helpful, you can always do that as well. This could be the conducting piece, which would be that wire right there. This piece connects from one battery, the negative end of one battery to the device. So that might be this. And then this connects the device to the positive end of the other battery. So that might be this. Since we're treating the wires as ideal wires that don't themselves have any resistance, you can draw your diagrams however you want, as long as they accurately represent, the reality. There's nothing to stop me from saying that this is my circuit diagram. This is still representative of exactly what is drawn on the left side of the page. It's a little weird. I don't know why you would necessarily draw it like that, but it is what it is. All right, so I've drawn my circuit diagram. Let's make sure everything is defined. So I have two batteries, each with a V. The positive ends are clearly identified. There's a resistor that has some resistance R, which I do know. And we want to make a guess. Now the next step is to make a guess as to the direction we think the current is going to flow. With series circuits, again, it is more straightforward. And you might try to convince yourself that it makes kind of intuitive sense that the current should be moving, in this case, in the clockwise direction. The next thing I would do is I need to pick a spot to be my start and end point. Maybe this time I'll do it up here. I'll have this be my start point and my end point. And then I draw my loop, and I'm going to go in the clockwise direction. I'm going to follow the current. You don't have to, as we saw. But that's how I'm going to draw my loop. So I complete one full loop. I'm back to where I started. Now I calculate my potential changes. First step, I go out, then I pass through the resistor. The current is going from top to bottom, and I've drawn the loop going from top to bottom. So I would write that as negative I times R. Then I go along the wire along the bottom. Then I go through the first battery, and I'm going from the negative end to the positive end. So we said that is plus V battery. And then I go through the second battery, and I go from the negative end to the positive end. So I would say that's again plus V battery. Then I get back, and I'm back to where I started. The loop law says I then set that equal to 0, which is step 4. Notice that this is an example where the batteries work together to provide a potential difference that is twice the potential difference as any one individual battery. So then I can solve for the current, and I get that as 2 VB over the resistance. So in that case, it would be 3 volts divided by, what did I say this was, 1.5 volts, or sorry, 1.5 ohms, so 2 amps. To be very explicit, the answer I get is plus 2 amps, which means I is indeed in the clockwise direction. We guessed correctly. I could ask, how much power is the LED screen drawing? I know in general, the power across any potential difference is just the current times V. So I could calculate, I now know what the current is. I could calculate how the potential is changing across the resistor, which again, for a resistor is just I times R. Or you get the equivalent formula of the power drawn from the resistor is just I squared times R. We just said I was 2, so 2 squared times 1.5. 2 squared is 4. Half of that is 2, so then this is 6 watts. And then again, not to be redundant, I could ask how much power was generated by the batteries. In that case, each battery is producing a power that is I times V, where this is V of the battery. This is V of the resistor. And the 2 is because there's 2 batteries. And we just calculated that that's 2, I was 2, and we're told that the voltage of each battery is 1.5 volts. Again, 6 watts. As it must be. Because again, this is just a statement of energy conservation. The power drawn from the resistor it's drawing 6 watts. So the battery better be providing 6 watts. Suppose I have, again, a battery. And now I'm going to have 2 batteries. The batteries are going to be connected to one another. One of them is a 1.5 volt battery, one is a 9 volt battery, and they're again connected to some resistor that, let's just say, has a resistance of 15 ohms. In this case, I've connected negative to negative terminal for the batteries. So the question is, what's going on here? First step, circuit diagram. So I have a battery, a resistor, and another battery. This is 1.5, this is 9, and this is resistance of 15. It's 1.5 volts, 9 volts. Again, if drawing colors helps, I'll let you convince yourself that this is what the circuit looks like. Now again, we just have a single circuit. There are no junctions. So if a steady state is set up, there must be only a single current throughout this entire loop. There can't be different currents at different parts of this loops, because again, that would violate charge conservation. There's no place where the charge is split off. First step is to make an educated guess to where the current is going to flow. This one is a little tricky because if you think of conventional current, the positive end of the battery is trying to push current forward, but now you notice that you have the 9-volt battery kind of pushing in the counterclockwise direction, the 5-volt battery is pushing in the clockwise direction. Which wins out? Let's just guess again clockwise and see if we're correct or not. The next step then is to draw my loop. Where have we not started before? I've always started here. So again, the loop I would draw, and I'll follow the current. Again, I don't necessarily have to. But here's what I'll do. And then I apply the loop law. So I start in the upper left. I go through the resistor. I'm moving through the resistor in the same direction as the current. So I will write that as minus IR. I then go down through the 9-volt battery, but I'm going from plus to minus. So then that is minus the voltage of the 9-volt battery. I then move back over to the left. Then I go up through the 1.5-volt battery. I'm moving from the negative to the positive end. That is plus the voltage of the 1.5 battery. And back to where I started, I set this equal to 0. Solving for I. Is pretty straightforward. V, so this is 1.5, this is 9, and the resistance is 15. So in this case, I get negative 0.5 amps. So again, what does the negative sign mean? It just means we drew the current in the wrong direction. The actual answer should have been that the current is going like this in the 9-volt battery and the 1.5 battery resistor. And this is exactly the setup. If the 1.5-volt battery was a rechargeable battery, this is how you recharge the battery. Essentially, you're driving a current from some sort of power source. Maybe it's another battery, like one of those small little pocket chargers you can have where you can hook up your phone to it to charge your battery in your phone from another battery that you have. That would be an example of this, where then current is driven from one battery to the other, but since the current is moving in the direction opposite, going from the plus to the minus terminal in the battery, power is actually being delivered to that battery instead of being taken away, like it is for the 9-volt battery in this case. So if this were a rechargeable battery where the chemistry inside the battery was set up where this is okay, this would recharge the battery. In practice, if it wasn't a rechargeable battery, then likely no current would flow. In that case, the potential difference would not be, it would be impossible to set up any sort of potential difference in the unrechargeable battery, and it would just be as if the circuit is broken. Alrighty. Last example, and then I'm done. It's the holidays. You have a string of Christmas lights. And they are attached to a 9-volt battery. And they're all connected in series. Let's assume each has, I don't think this is accurate, but let's just keep the math simple. Let's say it's 2 ohms. Each light bulb has 2 ohms, and you have a 9-volt battery. What is the current that is established in this case? And another question is, what is the equivalent resistance? Of all the bulbs. If you have a bunch of resistors in series, in this case there are a bunch of identical resistors, it'd be nice if I could replace this with a much simpler version where it has a battery and 1 resistor. That is incredibly simple to analyze. And we know the current is just the voltage of the battery divided by the equivalent resistance. But this is not what the circuit diagram looks like for this string of 6 Christmas lights. But maybe there's a way we can transform it so that it looks like this equivalent little diagram I've just drawn here. So first step is, of course, to draw the circuit diagram. So you have your 9-volt battery. It goes through the blue bulb, the green bulb, the red bulb, the other red bulb, the other blue bulb, the other green bulb, and back to the battery. Alrighty. Since there's only 1 battery, I'm going to make the educated guess that it's going to drive the current in the way that it wants. So I'm going to say that the current must be going in the clockwise direction. And I'm going to draw my loop following the current. Maybe I'll just have this again be my start and end point. So in this case, notice you're always passing through the resistors in the same direction as the current. So every time you pass through the resistor, it's minus IR, minus IR, minus IR, minus IR, minus IR, and minus IR. Then you move through the battery, going from the negative end to the positive end, so plus the voltage of the battery, and back to where I started. I set this equal to 0. Since these are all equivalent resistors, notice I could just write this as minus I times 6R plus V equals 0. Or that the current is the voltage of the battery divided by 6R. As the voltage of the battery is 9 volts, I said each of these was 2. This is 12 ohms. Let's see. They both can be divided by 3. So then I think this just becomes 3/4 of an amp. And you might notice by drawing a comparison between this and this, that the expression that we've written down in the lower left was just the sum of the resistors, and the sum of the resistors played the role of an equivalent resistor, as if this entire thing was just made up of one battery and one resistor. And I think I'll leave it to you to convince yourself that that is, in general, the case. For a series of resistors, our equivalent is equal to the sum of the individual resistors. Notice that looks kind of similar to what we had for capacitance, right? But be careful, because we said for capacitors in parallel, the equivalent capacitance is just the sum of the capacitances. It's flipped for the resistors. In this case, for a series of resistors, the equivalent resistance is just the sum of the resistances. And I will actually derive this next time, but just for comparison, for parallel resistors, 1 over R equivalent is equal to the sum of 1 over the individual resistors. So again, similar to something that we saw with capacitors, but they're flipped. For resistors, series, it's a sum. Parallel, it's the inverse sum. For capacitors, for parallel, it's a sum. For series, it's the inverse sum. All right, so next lecture will be much shorter, and it will just be me doing a couple more examples, but using parallel circuits, where then the current can branch off, and you have to not only take into account voltages and resistances, but the fact that there can be multiple lowercase i's flying around that you have to take into account as well. All right, very good.